January 23, 1944, somewhere over occupied France, 23,000 feet. Lieutenant Ray Murphy felt the shudder ripple through his P-47 Thunderbolt as German flak tore into the engine cowling. Two 40mm shells and one 20mm round punched through the radial engine in quick succession, obliterating two cylinders and fracturing the hydraulic system. Oil sprayed across the windscreen. The massive Pratt and Whitney R-28 Double Wasp engine, 18 cylinders of American engineering, should have seized immediately. The aircraft should have fallen from the sky. Instead, something impossible happened. The 16 remaining cylinders kept firing, the propeller kept turning. Chief Seattle, as Murphy had named his Thunderbolt, kept flying. 75 miles from base, Murphy nursed the crippled fighter home, touched down on a single blown tire, and skidded off the icy runway into a snow-covered field. He climbed out without a scratch. The Luftwaffe pilot who had witnessed the engagement must have been stunned. No German fighter could have survived that punishment. What that pilot didn't know was that he had just encountered the product of an American engineering philosophy so fundamentally different from German thinking that it would reshape the very nature of ground attack warfare. And the secret wasn't just in the robust airframe or the 850 caliber machine guns. It was in a 15-gallon tank mounted behind the engine firewall, filled with a water-alcohol mixture that German engineers had been experimenting with since 1934, but which American industry would deploy at a scale and with an effectiveness that would turn the stolid P-47 into something the Luftwaffe had never anticipated. A 400-mile-per-hour monster that could absorb catastrophic damage, deliver devastating firepower, and operate continuously at power settings that should have destroyed the engine in minutes. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The story of what made this possible begins not with the war, but with the peacetime work of two Pratt and Whitney engineers in Missouri. Arthur Smith and Donald Hersey understood a fundamental principle of internal combustion engines. Power output was limited by detonation, the uncontrolled explosion of the fuel-air mixture before the spark plug fired. Higher compression ratios meant more power from each combustion cycle, but higher compression created heat and pressure that caused spontaneous ignition. The fuel would detonate rather than burn in a controlled manner. These violent shock waves could destroy pistons, crack cylinder heads, and shatter connecting rods. Every piston engine designer faced this fundamental constraint. You could build a more powerful engine, but only if you could prevent detonation at the higher power settings. German engineers approached this problem through fuel chemistry, developing higher-octane aviation gasoline that resisted detonation better than standard fuel. British and American refineries followed suit, racing to produce 91 octane, then 100 octane, then fuels with performance numbers of 130 and eventually 150. But Smith and Hersey in 1938 had discovered a complementary approach. Inject a mixture of water and alcohol directly into the engine during high-power operations. The water absorbed heat from the compression process, lowering the temperature inside the combustion chamber. The alcohol prevented the mixture from freezing at high altitude, where temperatures could reach 60 degrees below 0 Fahrenheit. Together, they created an anti-detonation injection system that would eventually be designated ADI by Pratt and Whitney engineers. The chemistry was elegant. Water has an extraordinarily high heat capacity, meaning it absorbs tremendous amounts of thermal energy as it changes from liquid to vapor. When the water-alcohol mixture entered the supercharger intake, it vaporized, drawing heat from the compressed air. This cooler, denser charge entered the combustion chamber, allowing the engine to run at manifold pressures that would cause immediate detonation with dry air. The manifold pressure measured the boost provided by the turbo supercharger, the massive washing machine-sized compressor mounted in the P-47's tail cone. Normal military power settings on the R-2800 engine ran at 52 inches of mercury manifold pressure. War emergency power without water injection reached 60 inches. With ADI engaged, manifold pressure could climb to 70 or even 72 inches. The power increase was dramatic. A standard R-2800-21 engine generated 2,000 horsepower at military power. The same engine with water injection could produce 2,300 horsepower at war emergency power. Later variants with improved turbo superchargers and ADI systems reached 2,500, 2,600, even 2,800 horsepower in the P-47M and P-47 Newtons models. This wasn't an incremental improvement. This was a transformation of what the aircraft could do. But the system required careful engineering. The water-alcohol mixture, typically 50% water and 50% alcohol by volume, flowed from a tank through lines to injection nozzles in the intake manifold. Flow rate varied with power output. At 2,400 horsepower, ADI consumed 9.2 pounds of fluid per minute. At 2,500 horsepower, the rate increased to 11.5 pounds per minute. Even at high-altitude settings of 1,900 horsepower in high blower, the system consumed 7.8 pounds per minute. These flow rates meant the 15-gallon tank installed in early P-47D models provided only 5 to 6 minutes of boost. Pilots had to use ADI judiciously. Engage it for takeoff under heavy bomb load. Activate it during the critical moment of a strafing run when you needed maximum speed to escape German flak. Use it in combat when a German fighter threatened from an advantageous position, then throttle back to conserve the precious fluid. Later P-47D models, starting with the D-25 variant, doubled the tank capacity to 30 gallons, providing 12 to 15 minutes of war emergency power. But even this was a finite resource that required careful management. The introduction of ADI to P-47 operations occurred in stages. Early P-47B and P-47C models lacked the system entirely. The P-47C5, which entered production around July 30, 1943, received the R2-80059W engine, the W suffix indicating water injection capability. But factory installation of the complete system didn't begin until the P-47D4 and D5 production blocks. The Farmingdale factory started including ADI with the P-47D 10 inches late 1943. The Evansville factory followed with the D11 variant. Retrofit kits became available for earlier aircraft. P-47Ds from the D4 through D6 blocks could be modified relatively quickly, requiring about 200 hours of work per aircraft. Earlier models, including the D1 through D3 and the C2 and C5 variants, needed more extensive modifications. American fighter groups in England began receiving water injection-equipped Thunderbolts in January 1944. The 56th Fighter Group, which would become legendary flying only P-47 seconds throughout the entire war, received their upgraded aircraft that month. The 355th Fighter Group at Steeple Morden got theirs in February. Other groups followed through the spring. But the transition wasn't smooth. American crews had problems from the start. The issue was the alcohol. Pratt and Whitney had specified a mixture of ethanol and methanol combined with water. Instead, supply depots in England were providing the isopropyl alcohol, commonly known as rubbing alcohol. The difference seemed minor. All three alcohols prevented freezing, but the chemical properties varied significantly. Isopropyl alcohol formed deposits inside the injection system. It caused corrosion in aluminum components. Most critically, it didn't provide the same anti-detonation characteristics as ethanol-methanol mixtures. Engines experienced reduced power output, rough running, and in some cases, catastrophic failure. Pilots lost confidence in the system. Many refused to activate ADI during combat, preferring to fly without the boost rather than risk engine failure at a critical moment. Francis Gabreski, who would become one of the leading American aces in Europe with 28 victories, later recalled that early P-47 pilots viewed water injection with suspicion. The promised power increase seemed unreliable. Better to fly the aircraft within its proven limits than trust an experimental system that might destroy the engine. Pratt and Whitney dispatched Bill Kloss, one of their technical representatives, to England to investigate. Just before Kloss departed, Frank Walker, who reported directly to him, discovered the problem with isopropyl alcohol. Kloss confirmed in England that American depots were indeed supplying the wrong fluid. The mixture was changed to the proper ethanol-methanol water combination. The problems vanished. Engines ran smoothly at 70-inch manifold pressure. Power output met specifications. Pilots reported the acceleration was so violent it felt like the aircraft had been kicked from behind. The headrest would slam forward against the back of the pilot's head when ADI engaged. Robert Johnson, who would finish the war with 28 victories, all in P-47 seconds, later described his experience with his D-5 Thunderbolt, named Lucky. His ground crew had tuned the engine meticulously, adjusting the wastegates to maintain higher than normal boost pressure. The aircraft had been sanded, smooth at every joint, and waxed to a high gloss to reduce drag. With water injection engaged and throttle pushed forward to 72 inches of manifold pressure, the acceleration was breathtaking. Johnson claimed he never needed to use ADI in combat because his aircraft was already so fast. But when he activated the system just for the experience, the power was undeniable. The timing of ADI's arrival in European combat theatres was crucial. By early 1944, the strategic bombing campaign against Germany had reached a critical phase. American B-17 and B-24 bombers were conducting daylight raids deep into German territory. Luftwaffe fighter units, though severely depleted by losses over the previous year, still posed a significant threat. American fighter groups needed every advantage. The P-51 Mustang was beginning to arrive in theatre, offering superior range for escort duties. But P-47 groups retained their Thunderbolts and found a new role. Ground attack, the combination of robust construction, heavy firepower, and now dramatically increased low-altitude performance made the P-47 ideal for interdiction missions. Attacking German transportation networks, supply columns, airfields, and frontline positions required aircraft that could absorb punishment from ground fire and deliver devastating strikes against targets that often shot back. Water injection transformed the P-47's ground attack capabilities. At low altitude, where air density was highest, the power increase from ADI was most pronounced. A P-47, at sea level, running 60-inch manifold pressure, might reach 380 miles per hour in level flight. The same aircraft with ADI engaged could exceed 425 miles per hour. Some pilots reported indicated airspeeds approaching 450 miles per hour at full war emergency power. This speed advantage had profound tactical implications. German flak batteries protecting supply routes and military installations relied on predictable attack profiles. Anti-aircraft gunners calculated lead based on the speed and altitude of approaching aircraft. A fighter traveling at 350 miles per hour required a specific aiming solution. If that fighter suddenly accelerated to 425 miles per hour, the aiming solution became invalid. Shells exploded where the aircraft should have been, not where it actually was. The faster the aircraft moved through the flak envelope, the less time gunners had to track and fire. Each additional mile per hour of speed translated directly into increased survival probability. American pilots learned to approach targets at moderate speed to conserve ADI fluid, identify the target, set up the attack geometry, and then, just before entering the flak zone, push the throttle forward and engage water injection. The sudden acceleration carried the aircraft through the danger area before defensive fire could adjust. Deliver ordnance on target, pull up hard, throttle back to cruise power. The entire boost phase lasted perhaps 30 seconds. But those 30 seconds could mean the difference between returning to base or becoming another loss statistic. The German response to P-47 ground attacks evolved throughout 1944. Initially, Luftwaffe intelligence dismissed reports of Thunderbolts performing beyond their specified capabilities. German technical documentation captured in North Africa and Sicily provided accurate specifications for early P-47B and C models. These aircraft had maximum speeds around 430 miles per hour at altitude. At low altitude, performance was markedly worse. German flak units adjusted their tactics accordingly. But by spring 1944, Reports from German soldiers and flak crews began describing American fighters that seemed far faster than intelligence assessments indicated. Thunderbolts approaching at high speed, attacking before defenses could react, and escaping while still accelerating. Luftwaffe technical intelligence eventually obtained samples of the water-alcohol mixture from captured aircraft or abandoned drop tanks. Chemical analysis confirmed the composition. German engineers understood immediately what the Americans had achieved. ADI wasn't new technology. German aircraft had been using similar systems, designated MW50 for methanol water 50% mixture, since late 1943. BMW 801 radial engines in Focke-Wulf 190 seconds could use MW50 for emergency boost. Daimler-Benz DB 605 and Junkers Jumo 213 inline engines had comparable systems. But German implementation faced constraints that American operations did not. Production of MW50 fluid required methanol, which in turn required industrial chemical plants and distribution infrastructure. Germany's synthetic fuel industry, already stretched to breaking point producing aviation gasoline from coal, struggled to manufacture sufficient quantities of methanol water mixture. Distribution to frontline units became increasingly problematic as Allied bombing disrupted transportation networks. By late 1944, many German fighter units operated with minimal or no MW50 reserves. Even when fluid was available, usage guidelines restricted emergency boost to brief periods. German pilots activated MW50 for takeoff under heavy load or during critical combat situations. Continuous use would exhaust supplies within days. American P-47 units, by contrast, operated with effectively unlimited ADI fluid. Supply depots in England maintained massive reserves. Transport ships delivered hundreds of thousands of gallons monthly. Each fighter group stockpiled sufficient fluid for sustained operations. American pilots could use water injection liberally without worrying about conservation. If the 15-gallon or 30-gallon tank ran dry, ground crews simply refilled it. The next sortie would have full capability restored. This operational flexibility represented another dimension of American industrial superiority. Germany possessed the technical knowledge to match American ADI systems, but they lacked the industrial capacity and logistical infrastructure to deploy the technology at comparable scale. The contrast became most apparent during the Battle of Normandy. When Allied forces landed on June 6, 1944, American P-47 groups flew in support of ground troops. The 9th Air Force, which specialized in tactical operations, deployed hundreds of Thunderbolts for close air support and interdiction missions. These aircraft, many equipped with water injection, could respond rapidly to calls from forward air controllers. A German armored column moving to counterattack Allied positions would be spotted by reconnaissance aircraft or ground observers. Within minutes, a flight of 4 or 8 P-47 seconds would arrive overhead. The attack profile was devastating in its efficiency. Approach at medium altitude to conserve fuel. Identify the target. Roll into a 30 to 40 degree dive. Accelerate to terminal velocity using both gravity and engine power. With ADI engaged, the Thunderbolts would plunge toward the target at speeds approaching 500 miles per hour. At 1,000 yards range, open fire with all 850 caliber machine guns. The concentrated firepower, more than 100 rounds per second combined from all 8 weapons, would rake the target area. Armor-piercing incendiary ammunition penetrated vehicle armor, ignited fuel tanks, and destroyed equipment. At 400 to 500 feet altitude, pull out hard. 4 to 5 G load factor pressed pilots into their seats. The robust airframe handled the stress without issue. Then climb back to altitude, assess damage, and if necessary, make another pass. German forces on the receiving end of these attacks described the experience as terror weaponry. The distinctive whistle of air flowing through the P-47's engine cooling ducts and gun ports during a dive became an instantly recognizable sound. Soldiers learned to identify the noise and take cover, but there was often nowhere to hide. A P-47 strafing run left vehicles burning, equipment destroyed, and personnel casualties that could devastate a unit's effectiveness. The psychological impact extended beyond physical damage. German troops developed persistent anxiety about American air attack. Any aircraft engine sound triggered defensive reactions. Convoys moved only at night when possible. Daytime movement became increasingly hazardous. This disruption of German logistics had strategic consequences that matched or exceeded the direct destruction of equipment. The technical specifications that made this possible merit detailed examination. The R-2800 Double Wasp engine was a masterpiece of American engineering. 18 cylinders arranged in 2 rows of 9, air-cooled, with a displacement of 2,804 cubic inches. The engine weighed approximately 2,400 pounds installed. Pratt and Whitney had designed it for reliability and power output, optimizing for mass production while maintaining performance. The 2-stage turbo supercharger system, unique to the P-47, provided consistent power across all altitudes. Intake air traveled from the nose scoop through 43 feet of ducting to the General Electric turbo supercharger mounted in the tail cone. The spinning turbine, driven by exhaust gases, compressed the intake air before routing it back through an intercooler and into the engine. This system maintained sea-level air density at altitudes above 30,000 feet, allowing the engine to produce full power when German fighters experienced significant power loss. Adding water injection to this already sophisticated system multiplied its effectiveness. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The combat. Debut of water injection, equipped P-47 seconds, coincided with a dramatic shift in Allied air superiority over Europe. Between January and May 1944, before widespread ADI deployment, American bombers suffered loss rates of 3 to 6% per mission. These were sustainable but painful casualties. Fighter groups flew escort missions but faced range limitations and performance constraints. German fighters could often choose when to engage and when to break off. By June 1944, the situation had transformed. P-47 groups with water injection, combined with the arrival of long-range P-51 Mustangs, achieved air superiority that German fighters could no longer contest effectively. Loss rates for American bombers dropped below 2% per mission. Fighter groups claimed victories at unprecedented rates. The Luftwaffe, already weakened by years of attrition, faced annihilation. Ground attack missions told a similar story. Pre-invasion interdiction campaigns targeted French transportation networks to isolate the Normandy battlefield. P-47 seconds attacked rail yards, bridges, locomotives, and rolling stock. Each successful attack disrupted German logistics, delayed reinforcements, and constrained tactical flexibility. The effectiveness of these operations relied partly on ordnance. The 500 or 1,000-pound bombs carried on underwing pylons and centerline racks. But success also depended on the ability to survive the attack run. German flak defenses around critical infrastructure were formidable. Multiple batteries of 20mm, 37mm, and 88mm anti-aircraft guns created overlapping fields of fire. Approaching these targets at moderate speed was suicidal. But approaching at maximum speed with water injection engaged made the attack survivable, not safe, survivable. The distinction mattered to pilots who flew these missions repeatedly. The statistics from Normandy operations demonstrate the transformation. During the first weeks after D-Day, 9th Air Force P-47 groups flew thousands of sorties. On June 6 alone, Thunderbolts flew 2,398 combat missions. They claimed 84 German aircraft destroyed in aerial combat and 89 destroyed on the ground. More significantly, they paralyzed German ground movement through systematic interdiction. Vehicle columns attempting to reinforce the beachhead were caught in the open and destroyed. The Luftwaffe managed only 319 sorties over Normandy on D-Day. American fighters, including hundreds of P-47 seconds, flew over 13,000. The disparity wasn't just numerical, it was operational. German fighters possessed perhaps 200,000 rounds of ammunition total across all units in the theatre. American fighters carried millions of rounds with effectively unlimited resupply. German fighters operated under strict fuel conservation measures that limited sortie duration and combat aggressiveness. American fighters flew multiple missions daily, refueling and rearming between sorties without constraint. The P-47's role in the breakout from Normandy showcased water injection's tactical value. Operation Cobra, launched July 25, 1944, concentrated American ground forces for a breakthrough near Saint-Lô. The operation began with massive aerial bombardment. Heavy bombers saturated German positions. Medium bombers followed up with tactical strikes. Then P-47 seconds swept the battlefield, attacking any German forces attempting to maneuver. The ground support missions required precise coordination. Forward air controllers on the ground communicated target locations to orbiting fighter bombers. P-47 pilots would roll in, identify the target through the haze of dust and smoke, and attack. Water injection allowed rapid acceleration from orbit to attack speed. The faster the aircraft moved during the vulnerable approach phase, the better the survival odds. German troops caught in these attacks had no effective defense. Anti-aircraft fire was suppressed by the sheer volume of American firepower. German fighters rarely appeared. When they did, P-47 seconds could engage or evade as tactical circumstances dictated. Major John Motzenbecker's experience on December 17, 1944, during the Battle of the Bulge, illustrated both the capabilities and the risks. Motzenbecker led a flight of 4 P-47 seconds along the winding Prüm River, searching for German forces in the snowy landscape. The weather was marginal, with low clouds and limited visibility. German forces had launched their surprise offensive the previous day, creating a bulge in American lines that threatened to split Allied armies. Every available aircraft flew in support of ground troops struggling to contain the breakthrough. Motzenbecker spotted a road near the front lines and called for top cover while he descended to investigate. What he saw left him stunned. A massive German column stretched for miles. Tanks, half-tracks, trucks, horse-drawn artillery, all moving toward American positions. This was a target of opportunity that couldn't be ignored. Motzenbecker's flight attacked immediately. Diving from altitude, they engaged water injection to maximize speed through the flak envelope. German anti-aircraft fire filled the air. 20mm and 37mm shells burst around the diving P-47 seconds. Motzenbecker's guns tore into the column. Vehicles exploded. Ammunition trucks detonated in secondary explosions. The attack lasted seconds before the flight pulled up and climbed away from the intense ground fire. But the cost was immediate. Lieutenant Tom Easterling, flying as wingman to the flight leader, was caught in debris blown skyward by an exploding vehicle. Something, Motzenbecker later described it as looking like a piece of boilerplate, smashed into Easterling's aircraft. The engine immediately began smoking. Oil streamed from the cowling. The P-47 was mortally damaged. Easterling's wingman shouted over the radio, desperately hoping his friend could reach friendly lines. But the aircraft was losing altitude rapidly. Easterling belly-landed in German-held territory. He survived the landing and spent the remainder of the war as a prisoner. His P-47, even with its legendary toughness, had reached the limits of what it could absorb. The incident demonstrated both the effectiveness of P-47 ground attack and the lethal danger of low-altitude operations against defended targets. Water injection provided speed that increased survival probability. But probability wasn't certainty. German flak remained deadly. Ground investigations after successful attacks revealed the devastation P-47 seconds inflicted. A single mission on December 17th, the same day Easterling was shot down, resulted in 66 tanks, 204 vehicles, and 11 guns destroyed by strafing and bombing. These numbers represented not just equipment destroyed, but German mobility eliminated. Tanks that wouldn't reach the front, vehicles that wouldn't deliver supplies, artillery that wouldn't provide fire support. The cumulative effect of hundreds of such attacks, day after day, systematically destroyed German logistics. The 6th SS Panzer Army, which had been embarking on trains for transport to the Eastern Front, was caught by P-47 seconds on January 22, 1944. The 362nd Fighter Group flew into ferocious flak, ranging from 88mm guns to small arms fire. 5 P-47 seconds were lost. 4 pilots were killed. But the German armoured formation was devastated. Ray Murphy's Chief Seattle absorbed 2 40mm and 1 20mm shell hit that destroyed 2 cylinders, yet still brought him home. This pattern repeated across countless missions. P-47 seconds taking catastrophic damage yet continuing to fly. German ground forces learned that hitting a Thunderbolt didn't mean destroying it. The engineering that enabled this survivability extended beyond the robust R-2800 engine. The entire airframe was designed for damage tolerance. Dual redundant control systems meant that hydraulic failure didn't necessarily result in loss of control. Manual backup systems allowed pilots to lower landing gear and operate critical controls, even with complete hydraulic system failure. The air-cooled radial engine could lose multiple cylinders and continue running. Unlike liquid-cooled engines that would seize within minutes of coolant loss, the R-2800 tolerated significant battle damage. Pilots routinely returned to base with engines missing 2, 3, or even 4 cylinders. The remaining cylinders would run rough, generating vibration and reduced power, but they would run. This reliability under combat stress gave pilots confidence to press attacks that might be suicidal in less durable aircraft. The addition of water injection enhanced this confidence. Not only could the aircraft absorb damage, it could accelerate away from danger when needed. The German perspective on facing P-47 seconds evolved throughout 1944 and into 1945. Initial dismissal gave way to respect, then to fear. German soldiers described the psychological impact of hearing the distinctive whistle of diving Thunderbolts. The sound became associated with destruction and death. Units caught in the open would scatter for cover, but heavy vehicles, armoured fighting vehicles and tanks couldn't hide quickly. P-47 pilots learned to identify high-value targets and concentrate fire. Armour-piercing incendiary ammunition, though not designed specifically for anti-tank work, could penetrate lighter armour and set fuel tanks ablaze. Even heavy tanks were vulnerable to repeated hits. Engine compartments could be damaged, tracks could be broken, crew members exposed in open hatches could be killed. And if the tank survived the strafing run, follow-up attacks with 500-pound bombs would finish the job. German commanders complained bitterly about the impossibility of moving forces during daylight hours. Operations shifted increasingly to night movement. But this created its own problems. Night movement was slower, more difficult to coordinate, and vulnerable to ambush. The introduction of the P-47M variant in late 1944 represented the ultimate expression of water injection technology applied to the Thunderbolt. Republic Aviation set aside 4 P-47D airframes and fitted them with souped-up Pratt and Whitney R-28 0057 engines with CH-5 turbo superchargers. Together, these modifications generated 2,800 horsepower. The YP-47M prototypes achieved climb rates of 3,500 feet per minute and maximum speeds of 473 miles per hour in level flight. Some pilots reported achieving 490 to 500 miles per hour when using war emergency power with water injection. This made the P-47M arguably the fastest piston engine fighter to see combat in the war, though it was still slower than the Me-262 jet fighter's maximum speed of 540 miles per hour. The first P-47Ms, delivered in December 1944, were rushed to the 56th Fighter Group, the last 8th Air Force fighter unit still equipped exclusively with Thunderbolts. The aircraft began arriving on January 3, 1945, but the P-47M experienced significant teething problems. Engine failures caused several crashes. The improved R-280057 engine, operating at extreme power settings, pushed component limits. Pistons, cylinder heads, and connecting rods endured stresses that earlier models never experienced. Some failures resulted from manufacturing defects, others represented the inevitable consequence of pushing technology to its absolute limit. By March 24, 1945, engineers had resolved the problems. The 56th Fighter Group commenced combat operations, with the P-47M. On March 25, Major Bostwick, commanding officer of the 63rd Fighter Squadron, led his flight on a ramrod mission over Hitzacker, Germany. Flying P-47M-1RE, serial number 44-21160, nicknamed Devastating Deb, Bostwick pursued German jet fighters fleeing eastward toward their base at Parchim. The P-47Ms could reach 490 miles per hour with water injection engaged. Even this speed wasn't enough to catch the Me 262 seconds in level flight, but jets were vulnerable during landing approach, when speed dropped and maneuverability decreased. Bostwick lined up on an Me 262 on final approach. The jet pilot, recognizing the danger, didn't land. Instead, he continued flying down the runway and flew directly over another Me 262 that was taking off. Bostwick shifted his gun sight to the departing jet and fired a burst just as the German pilot broke left. The combination of the tight turn and low altitude proved fatal. The pilot dug the jet's port wing tip into the ground. The fuel-laden Me 262 cartwheeled and exploded. This engagement demonstrated both the capability and the limitation of even the hottest P-47 variant. Against jet fighters, the Thunderbolt could compete only by exploiting the jet's vulnerability during takeoff and landing. In level flight at altitude, German jets possessed a speed advantage that piston-engine fighters couldn't overcome. But jets remained rare. Most German fighters in early 1945 were conventional piston-engine aircraft flown by pilots with minimal training and limited fuel. Against these opponents, the P-47M was devastatingly effective. The combination of speed, firepower, and now extreme power output made it nearly impossible to counter. The Pacific Theater saw its own evolution of P-47 water injection operations, though on a different timeline and with different tactical requirements. P-47 seconds began arriving in the Central Pacific in mid-1944. The 318th Fighter Group, operating from Saipan, flew ground support missions during the island assault and then began offensive operations against Japanese positions on Guam and Tinian. These missions emphasized ground attack more than European operations initially had. Japanese air opposition was sporadic and decreasing. The real fight was against fortified positions, supply dumps, and the remnants of Japanese forces holding out in difficult terrain. P-47 seconds with water injection could carry heavy bomb loads, accelerate rapidly during attack runs, and survive hits from Japanese anti-aircraft fire. The ruggedness that served so well in Europe proved equally valuable in the Pacific, but the Pacific posed unique challenges. Long over-water flights required maximum range. The P-47D variants initially deployed had insufficient fuel capacity for very long-range escort missions. Republic responded with the P-47 Newtons, featuring an extended wing that held an additional 93 gallons of fuel internally. Total internal capacity reached 556 gallons. With full internal and external drop tank fuel, totaling 1,266 gallons, a P-47 Newtons could fly 2,350 miles. With water injection and the improved R-280077 engine generating 2,800 horsepower, the P-47 Newtons could reach 470 miles per hour maximum speed. 3 new fighter groups, the 413th, 414th, and 507th, activated specifically for Pacific very long-range operations in October 1944. These units received P-47Ns and trained for missions escorting B-29 superfortresses to Japan. The 413th and 507th fighter groups began operations from Shima in May and July 1945, respectively. The 414th arrived at Iwo Jima in July. They flew ground attack missions against Japanese targets in the home islands, Korea, and China. These missions lasted hours, testing pilot endurance and aircraft reliability. Water injection allowed maximum performance during the critical combat phase while conserving fuel during cruise segments. American pilots would fly at efficient cruise power for the long transit to the target area. Once over Japan, they would descend to attack altitude, engage ADI, and strike with maximum aggression. Then they would disengage, climb to altitude, throttle back to cruise power, and make the long flight home. This operational profile demonstrated the tactical flexibility that water injection enabled. The same aircraft could function as a long-range cruiser and a high-performance attack aircraft simply by managing power settings and ADI usage. The war ended before Pacific P-47 operations reached their full potential. By August 1945, when Japan surrendered, very long-range P-47 Newton's units had flown only limited combat missions. But the lessons learned in Europe applied directly. Water injection transformed the Thunderbolt from a good fighter into an exceptional ground attack aircraft. The ability to operate at extreme power settings, absorb heavy damage, and continue fighting made the P-47 irreplaceable in the tactical role. German forces learned to fear the distinctive whistle of diving Thunderbolts. Japanese forces faced the same terror in the war's final months. The psychological impact matched the physical destruction. Ground troops developed anxiety disorders from repeated air attacks. The stress of knowing that any movement, any exposed position, could attract a devastating strike from aircraft that seemed immune to defensive fire. This stress eroded unit cohesion and combat effectiveness in ways that exceeded simple casualty statistics. American industrial capacity made this possible. The technical sophistication of water injection systems was impressive, but many nations possessed engineers capable of developing similar technology. Germany had MW-50 systems. Britain experimented with various boost technologies. The Soviet Union captured German equipment and examined it carefully. What separated American operations from all others was scale. Republic Aviation's factories produced over 15,000 P-47 seconds during the war, more than any other American fighter. The Farmingdale factory covered 765,000 square feet. The Evansville factory added massive additional capacity. Combined output reached over 400 aircraft monthly by late 1943. Each aircraft received its full complement of equipment, including water injection systems on later variants. Retrofit kits were manufactured by the thousands to upgrade earlier aircraft. Ground crews received training in ADI system maintenance and operation. Supply chains delivered thousands of gallons of water-alcohol mixture monthly to every base operating P-47 seconds. This logistics infrastructure, invisible but essential, ensured that tactical capabilities translated into operational effectiveness. German industry, by contrast, struggled with dispersed production, material shortages, and relentless Allied bombing. German fighter production actually peaked at over 25,000 aircraft annually in 1944. But fuel shortages meant many never flew operationally. Those that did flew with reduced armament to save weight, limited ammunition to conserve resources, and strict fuel management that constrained tactical freedom. MW-50 availability was sporadic at best. Distribution to frontline units became increasingly difficult as transportation networks collapsed under Allied air attack. By early 1945, German fighter units often operated without any boost fluid reserves. They had the aircraft. They had the technical knowledge. But they lacked the industrial capacity and logistics infrastructure to sustain operations. This fundamental disparity decided the air war's outcome more surely than any single technological advantage. The P-47 with water injection was superior to German fighters in multiple dimensions. But even without water injection, American numerical superiority and operational sustainability would have achieved air supremacy eventually. Water injection accelerated the process and reduced American casualties by providing tactical advantages that compounded over thousands of missions. The human cost of these operations appears in the statistics, but is really told in individual stories. Lieutenant Edwin Wright of the 404th Fighter Group completed 39 missions supporting the Allied advance into northwest Europe by October 1944. He had been hit by flak 6 times. His aircraft bore scars from each encounter. On one mission, a flak shell tore an 8-inch diameter hole in his propeller. If the damage had been 1.5 inches to either side, the blade would have severed and Wright would have crashed. Instead, the P-47's robust construction and the propeller's remaining strength allowed him to return to base. He landed safely, and the aircraft returned to combat after repairs. This pattern repeated across hundreds of pilots and thousands of missions. Aircraft that should have been destroyed made it home. Pilots who should have been killed survived. The margin between life and death often came down to the P-47's ability to absorb punishment that would destroy any other single-engine fighter. Water injection added another layer of survivability by allowing rapid escape from dangerous situations. But not every pilot was lucky. Tom Easterling became a prisoner of war. Countless others died when their aircraft finally took one hit too many. Flak remained lethal regardless of aircraft type. The P-47's durability improved survival odds but couldn't guarantee it. Pilots flew, knowing each mission might be their last. They relied on their aircraft's strength, their own skill, and the support of wingmen to survive. Water injection gave them one more tool. In the calculus of aerial combat, where margins are measured in miles per hour and fractions of seconds, every advantage mattered. The 40 or 50 additional miles per hour that ADI provided could mean escaping a flak burst that otherwise would have hit. It could mean catching a fleeing German vehicle before it reached cover. It could mean pulling out of a dive with enough altitude margin to avoid hitting the ground. These small advantages accumulated across thousands of missions into strategic impact that helped decide the war's outcome. Technical innovations like water injection represented American engineering culture at its finest. Pragmatic solutions to identified problems. Systems designed for reliability and maintainability under field conditions. Technologies scaled to industrial mass production without sacrificing quality. The contrast with German engineering philosophy was stark. German designers pursued technical perfection, creating weapons that were often superior in isolated metrics, but difficult to manufacture and maintain. The Messerschmitt Me 262 was faster than any Allied fighter. The Tiger II tank had heavier armor than any Allied equivalent, but these weapons arrived in small numbers, often too late to affect outcomes, and proved difficult to support logistically. American weapons were usually not the best in any single category. The P-47 wasn't the fastest fighter, it wasn't the most maneuverable, it wasn't the longest ranged until the P-47 Newtons arrived, but it was very good in all categories. It was producible at mass scale. It was reliable. It was maintainable by mechanics with moderate training using standard tools, and it was effective when flown by pilots with reasonable skill. These qualities, less glamorous than record-breaking performance numbers, decided wars. The legacy of P-47 water injection extends beyond World War II. Modern military aircraft continue to pursue performance enhancement through various means. Afterburners on jet engines provide thrust boost similar in principle to ADI, burning extra fuel to generate emergency power. Trade-off between capability and resource consumption remains fundamental to tactical aviation. The A-10 Thunderbolt II, named in honor of the P-47, embodies similar design philosophy. Not the fastest aircraft, not the most sophisticated, but rugged, reliable, heavily armed, and devastatingly effective in the ground attack role for which it was designed. The lessons learned from P-47 operations in World War II influenced multiple generations of aircraft designers. Survivability matters, weapons load matters, operational sustainability matters. Raw performance numbers matter less than effectiveness under real combat conditions. The P-47 demonstrated these principles through hundreds of thousands of combat sorties across 2 theaters. Water injection was one element in a comprehensive system that proved superior to anything German industry could field. The final accounting of P-47 achievements tells the story in numbers that still astound. Thunderbolts destroyed 3,916 enemy aircraft in aerial combat. They destroyed 3,200 enemy aircraft on the ground. They destroyed 9,000 locomotives, 86,000 railway cars, 68,000 motor vehicles, and 6,000 armoured fighting vehicles. They flew more than 500,000 combat missions. They dropped 132,000 tons of bombs. They fired 135 million rounds of 50 caliber ammunition. They launched 59,565 rockets. These statistics represent strategic impact beyond tactical success. German transportation infrastructure destruction by P-47 seconds reduced Wehrmacht mobility and logistics capability dramatically. The Luftwaffe's inability to counter P-47 ground attacks meant American air power operated with near impunity across Western Europe from mid-1944 onward. The cumulative effect was German defeat in the air, which enabled Allied success on the ground, which ultimately determined the war's outcome in Europe. Water injection was not solely responsible for these achievements. The P-47's 850 caliber machine guns provided firepower that German fighters couldn't match. The rugged airframe and reliable R-2800 engine provided survivability that German fighters lacked. American pilot training, which gave new pilots 400 or more flight hours before entering combat compared to German pilots who often had less than 100 hours, provided skill advantages that tactical innovations amplified. American numerical superiority, with multiple fighter groups operating hundreds of aircraft compared to Luftwaffe units barely able to field squadron-strength formations by late 1944, provided overwhelming force that no German tactical expertise could counter. But within this context of cumulative advantages, water injection provided a specific, measurable enhancement that transformed tactical capabilities. The 40 to 70 miles per hour speed increase at low altitude where ground attack missions operated made the difference between acceptable losses and unsustainable casualties. The ability to engage ADI for 30 seconds to 1 minute during the critical attack phase turned dangerous missions into survivable ones. German pilots and ground troops who faced P-47 seconds recognized this capability even when they didn't understand its source. They knew that American fighters seemed faster than specifications indicated. They knew that Thunderbolts could accelerate away from trouble with shocking rapidity. They knew that attacking American ground forces brought swift retaliation from aircraft that seemed nearly indestructible. This knowledge affected German tactical decisions at every level. Ground commanders avoided daytime movement. Luftwaffe controllers husbanded fighter resources rather than commit them to battles they would lose. German soldiers developed anxiety about American air superiority that reduced combat effectiveness, beyond what casualty statistics would suggest. The psychological dimension of American air dominance, expressed through weapons like the P-47 with water injection, contributed to German defeat as surely as physical destruction of equipment and personnel. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.